Okay, welcome everyone to Physics 390 class 27. This class is on Fermi's golden rule and the adiabatic approximation. So Fermi's golden rule is a rule for transitions between a discrete quantum state and a narrow band around a continuum band around a final state. And the adiabatic approximation and the adiabatic theorem has to do with what happens in physics and in particular quantum mechanics when the external conditions of a system change in a very gradual way, and what happens to the eigenstates of the system and what happens to the energies of the system in that case. So actually two kind of different results, Fermi's golden rule and the adiabatic approximation together in this video. And this is from chapters 11.4 and 11.5 of our textbook. All right, so here we go. Fermi's golden rule. So, so far we've been looking at transitions between two discrete states, A and B. For example, two states in the infinite square well, which are discrete quantized states. But they're also continuum states or scattering states. So suppose there's a transition from an initial discrete state I, for example, a bound state of the hydrogen atom, say, to a continuum of states near state F. For example, if the hydrogen atom got ionized, then it would go from a bound state to a state in a continuum of states, a free particle state for the electron that would travel away from the atom. So in this case, we can show the transition probability is given by the following. And there's an argument for this in the textbook, that the probability P of transitioning to this continuum of states near state F is 2 pi over h bar times the matrix element VIF over 2 squared times rho of EF, where rho of EF is the density of states at EF, times T. So the probability increases linearly in time. So again, VIF here is the matrix element of the perturbation V, which is driving the transition between state I and state F. Meanwhile, rho of EF here is the density of states at energy EF of the energy EF of state F. So what do we mean by the density of states? Well, we mean that by this we mean the number of states in a small range DE around EF would be the density of states rho of EF times DE. So we have to multiply a small interval by this density of states to get the total number of states. That's why it's called the density of states. So the units of density of states rho EF would be 1 over energy. It's the density of states per unit energy. Okay, so since the probability P for the transition is linear in T, we can write the rate of transition unambiguously as just the coefficient of T, which is 2 pi over h bar VIF over 2 squared rho of EF. So it's a pretty nice compact expression. I mean, it's 3 terms and none of them are overly complex. There's no square roots or logarithms in here. There's just a squared. This is known as Fermi's golden rule, which is the title of our slide here. And so Fermi's golden rule again applies when we have transitions from a discrete state I to a state F, which is part of a continuum of states. So it's a continuum of states, free states or scattering states that is the final destination state. And the greater the matrix element VIF, and the greater the density of accessible final states near EF, so the greater rho and the greater VIF, the faster the transition rate will be, which makes sense. The greater the interaction and the more places there are for the interaction to send the initial state, the faster the transition rate will go. So that's Fermi's golden rule. That's how it works. So let's check out an example of Fermi's golden rule, just to see it in action. So suppose we have a particle of mass m and wave vector k prime. So that's the wave vector is 2 pi over lambda, and it's a vector, so it's directed in the direction the particle is traveling, in the direction of the velocity, and it's scattering from the potential v of r. Okay, so we take a box of a significant side length L to contain the interaction. And the reason we do that is because we want to have normalized states. And if we contain things in a box of length L, we can normalize the wave vector, the eigenstate associated with the wave vector k prime. So the normalized initial and final states are psi initial is e to the I k prime dot r. So that's a traveling wave with wave vector k prime. And it's 1 over the square root of L cubed, the square root of the volume. So if we integrate this over the entire volume, we get 1, which is the normalized state. Meanwhile, psi f is going to be, it's going to scatter into a wave vector k. So the incoming wave vector is k prime. The outgoing wave vector is k. We get 1 over square root of L cubed e to the I k dot r. So that's the final state. Okay, so the matrix element we're looking for is V Fi, would be the integral of psi f star V psi I. That's the matrix element written out in integral form. And if we take these psi f here, that this e to the I k becomes e to the minus I k because it's psi f star. So we get e to the minus I k dot r. Here's our e to the I k dot r here. Then we have our v of r in there. And then the 1 over square root of L cubed, the 1 over square root of L cubed become a 1 over L cubed out in front. So this is our matrix element here for the interaction between the initial and final states, these wave vectors coming in. The density of states can be shown, and see the text for this because it's about a page of arguments, to be rho of E is something to do with the volume of the box, which makes sense. The bigger the volume of the box, the more energy states there will be, times this factor, which is proportional to the square root of E. So the higher the energy, the more states there are per unit energy interval. And then also it's multiplied by the solid angle d omega, because remember these wave vectors are scattering somewhere in space. So the bigger the region of angles we give, the bigger the more energies there are that will go into those angles. So that's the density of states. So we can combine these two according to Fermi's golden rule. Combining according to the FGR of Fermi's golden rule gives the rate for the initial state scattering into the final state, which would be the region of solid angle d omega, where the k vector points somewhere in d omega, would be 2 pi over h bar, which is the first factor, times the second factor, which is VFI squared, times the third factor, which is rho of E, which is this factor here. So I have 3 factors: 2 pi over h bar, VFI squared, and rho of E. So those are all together now, together here. So that's interesting. It's a little bit messy, but it's certainly an interesting rate. It's something we wouldn't have known how to calculate before, and now we've got an exact expression for it. The differential cross-section is, remember the differential cross-section measures how much area of the incoming beam goes into a given solid angle d omega. So the area of the incoming beam is d sigma going into d omega, the solid angle of exit from the scattering process. So if Ji is the incident particle flux that's coming in, so we have now a bunch of particles coming in, and we have the particle flux means the number per unit area per unit time. That's flux per unit area per unit time. So that would be the differential cross section. Then would be the rate of transitions from the initial state to the solid angle divided by the solid angle divided by the incident particle flux, okay? So that's because if we doubled the incident particle flux, we expect the rate to double because we'd have more particles which could make this transition. So R is going to be proportional to JI. Not only that, but the units work out. The dimensions are correct. So if you look at this, let's see. So, well, first of all, we have d omegas in both denominators. So that's those units work out. They actually, d omega doesn't have any units, but it appears in both denominators. And then the R is a rate 1 over time. Ji is 1 over area times time. So that'd be 1 over time divided by 1 over area time. So the whole thing would be area, but d area in the numerator. But d omega is, or d sigma is an area. It's the incoming area of the beam. So we have area equals area, and the dimensions are correct. So we can at least believe that this formula is plausible, even if we haven't fully proved it here. So writing this out, dividing this by JI, there's an expression for JI in the textbook, and doing some algebra leads to the following expression for the differential cross-section for this scattering of a particle K with wave vector K prime off of V of R, where it scatters into the wave vector K in a given direction. It's given by this expression here. And coincidentally, or interestingly, this actually matches the first Born approximation, which we looked at in a previous video. The Born approximation using the integral form of the Schrodinger equation. What's in the brackets here is the differential, sorry, the scattering amplitude, f, theta, and phi. And then the square of that is the differential cross section. So this matches what we get in the first Born approximation. And we know that the first Born approximation is very accurate for weak scattering potentials. So we can say that the result we get here from Fermi's golden rule is generally useful, but would be especially accurate for weak scattering potentials, V of R, where the energies are not, the particles are not too violently scattered by the potential. Okay, so that's an example of applying Fermi's golden rule, and we get something which agrees with what we had before. So gives us some confirmation that Fermi's golden rule makes some sense. All right, great. Let's move on to the adiabatic, the second part of this video, the adiabatic approximation and theorem. So what does adiabatic mean? Adiabatic means that the external conditions of a system change gradually, so the character of the system's behavior does not change. Okay, that seems a little bit general, so let's be a little more specific. So suppose our system is a pendulum, and the pendulum, the external conditions that are changing is the very slowly changing length of the pendulum, L of t. Okay, now the character of the pendulum's behavior, one character of it is the period P of t, P of P is 2 pi square root of L over G. So if the length, the external conditions, the length changes very gradually, then the period will change this formula will still hold at all times t. So the period as a function of t will be the same expression that holds for constant L, just with L of t. Since L of t varies slowly, we can say P at time t, the period at time t, will be 2 pi square root of L at time t over G. So that's what meant by saying the character of the system's behavior doesn't change, because it's still changing in time, but this form of the expression for the period in terms of L is not changing. Okay, so that's general. That's actually classical mechanics. In quantum mechanics, or QM, we have what's called the adiabatic theorem. So it says if the Hamiltonian, the energy operator, changes gradually from H0 to HT, H at time 0 to H at time capital T, then the nth eigenstate of H0 is carried into the nth eigenstate of HT. So the eigenstates, all the eigenstates smoothly vary from the original Hamiltonian to the final Hamiltonian, as opposed to if the Hamiltonian is changed rapidly, it can mix eigenstates. The eigenstates of H of T, if the change happens gradually or quickly, it can be linear combinations of the eigenstates of H0. But that's not the case here. The eigenstates very smoothly and do not mix. That's the adiabatic theorem. So as an example, for a particle in an infinite square well here we have a particle in a square well of length A, and here's our ground state, which goes to 0 at both edges, as we are familiar with. Suppose we double the size of the well. Okay, in the second picture here, we've doubled the size of the well gradually. So we've taken this wall and we've moved it out really, really slowly. So the external conditions of the system are changing gradually. The Hamiltonian is changing gradually as the parameter A changes very gradually. And so this eigenstate, the ground state eigenstate, changes smoothly into this ground state eigenstate here. On the other hand, if in the third picture here, we've very suddenly shifted the wall from A out to 2A. So we shift it out to 2A. Now, if we suddenly shift it, the system doesn't have time to respond. So it will stay in this, the same wave function it was in at the start, which was the ground state eigenstate. But now that same wave function with a width of 2A is no longer the ground state eigenstate. In fact, it's to write this wave function, it would have to be a mixture of a lot of different states. So we can see that this process, to the second picture, would be the adiabatic process. This would be the sudden process, where the adiabatic theorem would not apply. Okay, a couple other things can happen here to state the full adiabatic theorem. The phase actually changes. It becomes a dynamic phase because as the Hamiltonian changes gradually, not only the eigenstates change, but the energies En change in time. So the time-dependent factor e to the minus I En t over h bar, En independently changes in time. So En becomes a function of time. So we can write that as e to the I phi or theta n of t, where theta is now the integral from 0 to t of En t prime dt prime. So so that's a generalization of this phase factor here for when En is a function of time. And that's called, this e to the I phi n of t is called the dynamic phase. If En is constant, it reduces to the regular phase, but it's the dynamic phase in general. Okay, we can have a geometric phase in addition, which is a phase which comes about because of a change in the geometry of the system. So that can happen. We won't go into that in too much detail here, but that happens in certain systems. So the general statement of the adiabatic theorem is that psi n of t is the dynamic phase times the geometric phase, if it exists, times the wave function. Notice the phase doesn't affect direct measurements because when we take the expectation values or the amplitude squared, we do not get, the phase doesn't enter, but it could affect interactions, okay? Could affect interactions. So the phase could be important if it's interacting with another field or another particle. So watch out for those phases in certain cases. Okay, let's see an example of an adiabatic theorem. So we have an electron spin here at the origin. Here's an electron with a spin in it, and it's in the presence of a rotating magnetic field. Here's the magnetic field. Magnetic field is banked at an angle alpha with respect to the z-axis. It's rotating around with angular frequency omega counterclockwise around the z-axis like this. So the magnetic field is rotating around. What does the spin do? Well, let's assume this electron starts spin up along B at t equals 0. So here's B at t equals 0. So it's spin up there. So that spin up state would be cosine of alpha over 2, sine of alpha over 2. Just to check that, if alpha equals 0, which would correspond to the B field being in the z direction, then alpha equals 0, cosine of 0 is 1, sine of 0 is 0. So we would get chi equals 1, 0, which is the SZ plus state, okay, which is what we'd expect. On the other hand, if we're in the XY plane, or say along X, for example, then alpha would be pi. Pi, this should be pi over 2. Not pi, but pi over 2. So then cosine of pi over 2 would be cosine of pi over 4, which is root 2 over 2. Sine of pi over 2 is sine of pi over 4, which is root 2 over 2. So we get chi equals root 2 over 2, root 2 over 2, which is the eigenstate of Sx, the spin up Sx. So it matches in those two cases. Okay, so after some work with the TISE, the time-independent Schrodinger equation, using this interaction between the spin and the rotating magnetic field, we can find the probability of transition. You can check the text for this, to spin down to be given by this. It's the inner product of spin down with our time-dependent spin, and it's equal to this expression here, omega over lambda, sine of the angle, sine lambda t over 2 all squared, where omega is the frequency of rotation, and lambda is defined as this quantity here, which involves the angle and the rotating frequency of the magnetic field omega, also omega 1. Now, omega 1 is the Larmor frequency. It's the frequency that the spin would precess around the magnetic field. It's E B0 over M. Okay, so all right, so what does this have to do with the adiabatic theorem? Well, if omega is much, much less than omega 1, then we have lambda will be approximately equal to omega 1. Okay, since here omega squared would be very small, and omega 1 would be much smaller than omega 1 squared. So lambda here would be approximately be omega 1. And in that case, if we look up here, we have in the transition probability to spin down, we'd have omega over lambda, but lambda is omega 1, and omega over omega 1 is going to be very small because omega is much, much less than omega 1. So this whole thing, and then it's squared, so it gets really, really small. So the probability of transition to spin down becomes negligible in this case, where omega is much, much less than omega 1. So the adiabatic theorem applies, where the frequency of the field is slow compared to the Larmor frequency. Then the slowly changing field B of t carries along the spin-up eigenstate with it. There's no probability of transition to spin down. It just stays in that spin-up state as the B field goes around, where the spin-up state changes orientation as it goes. Okay. On the other hand, if omega is much, much bigger than omega 1, so this is spinning really fast, then omega 1 squared and omega 1 would be small. So this lambda would be omega. So we'd have omega over omega, which is 1, and we get a oscillating probability. So the probability of transition to spin down oscillates in time. And so that's very different. So that's a non-adiabatic situation. Okay, so that's an example. The adiabatic theorem holds when omega is much, much less than omega 1. The external condition, the magnetic field to the system, is changing slowly, and it stays in that same spin-up eigenstate. It's just carried along with the external condition. Okay, so just a quick summary. We looked at Fermi's golden rule, which connects discrete initial states with continuum states in transitions. We looked at a particular case of that, scattering off of a potential by an incoming wave. We saw we got a reasonable result that agreed with the Born approximation, the first Born approximation. And then we looked at the adiabatic nature, where external conditions change slowly. We saw the adiabatic theorem, which involved phase, and we looked at an example of the adiabatic theorem for a spin interacting with a magnetic field. Okay, so two kind of different phenomena here, Fermi's golden rule and the adiabatic theorem, but both very interesting. And I hope this has given you some more insight into quantum transitions and the time-dependent behavior of quantum systems. All right, thanks for your attention, and I'll see you in class.